Hello, I'm Yingwei. Today I'm going to introduce our work, Regional Homogeneity Towards Learning Transferable Universal Adversarial Perturbations Against Defenses. This is a joint work with Song Bai, Cihangxie, Zhen Yuliao, Xiaohui Shen, and Alan Yu. Deep learning models are good at several computer vision tasks such as image classification. However, if the attackers add some small perturbations to the original image, the model will be fooled. To achieve this, attackers need to know all the details of the target model. This makes the attack method challenging to apply to real-world scenarios. Several previous works make the adversary examples transferable. This means they can fool not only known models but also unknown models. However, when the attackers meet an unknown defense models, previous method will fail. The defense model means the model is specifically designed for defending adversary attacks. Our work will address the issue of how to attack defense models. We start from a very basic question: why adversary examples for average models cannot transfer to defense models? The secret is that they look very different. According to the right image, the first row is an adversary example for natural models, while the second row is for defense models. We observe that every pixel of the perturbation for defense models are locally similar to its neighboring pixels. We term this property as regional homogeneity. This property can be widely observed on many different kind of defense models with different kind of attacks and different kind of tasks and data sets. Therefore, to attack defense models, we need to construct regional homogeneous perturbations. We start by editing a very popular adversary attack models, fast gradient sign method, FGSM in short. For each target image, FGSM computes the loss gradient and then add it back to the original image. We insert a gradient transformer before applying the gradient to the original image, and then maximize the classification loss to train the parameters of the gradient transformer. This gradient transformer will make sure the perturbations are regionally homogeneous. Why can it make sure the regional homogeneity? Let's go to the details of the gradient transformer. It consists of a one-by-one convolutional layer and a region norm layer. The region norm will first split the image into several regions and normalize each region independently. With the help of region norm, the pixels in the same region will influence each other. We show the methods in our paper. Then we found our perturbations are universal, just like the right figure. For any images, after adding a fixed perturbation, the prediction result will be incorrect. Concretely, we found the well-trained gradient transformer module will output an almost fixed output, no matter what the input is. We found the value of B is significantly larger than A, while C is significantly larger than D. This indicates the input gradient G won't influence the output gradient G hat. What's the reason? Why can it be universal? Because of underfitting. The figure shows you the situation of the extreme underfitting and overfitting with the regression problem. When overfitting, the curve will perfectly fit every data, but the variance is large. On the other hand, when underfitting, the variance is almost equal to 0. We only have less than 1,000 parameters in our model, but we have 5,000 images for training. Considering the number of parameters is significantly less than the number of data, our model output pattern will be similar to the underfitting figure. Therefore, we can generate universal perturbations. In the experiment part, we validate the connection between universal and underfitting. When we use fewer images for training, we cannot observe B significantly larger than A and C, or C significantly larger than D, so that it's no longer universal. This observation is consistent with the previous analysis. Our perturbation successfully attacks defenses. We test our perturbation with 9 state-of-the-art defense models. Our universal perturbations are stronger than others, even stronger than input-dependent perturbations, which could utilize more information than universal perturbations. The quantitative results are also interesting. Although we conducting non-target attacks, we found the region split function is related to the target categories. For example, when we use the vertical split function, the perturbation will also be vertical. After adding the vertical perturbation to the clean image, the image will be classified as harp, window screen, or theater curtain. All of them consist of vertical patterns. This observation further supports the hypothesis that the ImageNet trained deep neural networks are biased towards textures. Our perturbations are also extendable. For example, our perturbations also have strong cross-task transferability. We generate adversarial perturbations for segmentation models. Finding these examples can also successfully attack object detection models. In summary, we conduct regional homogeneous perturbations that can universally fool the defense model. We also provide another alternative to generate universal perturbations. We visualize our perturbation and attack results, finding deep neural networks are slightly over-relying on textures. Our method is very general. For example, our method also serves as a strong attacker of cross-task attacks. Thanks for your attention. Please check out our paper and code for details.